Hello everyone, my name is Lucas Ferreira, and I'm here to talk about the work I did with Levi Lelis and Jim Whitehead. And the work is called Computer-Generated Music for Tabletop Role-Playing Games. 3 years ago, we introduced a system called Bardo, and that system selected background music for tabletop RPG players. It worked by taking the player's speeches and using a speech recognition system to generate the captions, which we use to train an emotion classifier. The emotions from this classifier would be used to select hand-authored music pieces, which would be then played to the players while they were playing the game. This year, we introduced a new system called Bardo Composer, which is based on the previous one, but now instead of selecting music pieces, we generate completely new music for the tabletop RPG players. Initially, the system works the same. So it starts with the player's speeches. It also uses a speech recognition system to generate the captions. Again, we have a story emotion classifier. But the new contribution of this paper is an algorithm we call stochastic bi-objective beam search, where we combine a language model and a music emotion classifier to generate music pieces with given emotions. Let me start talking about the dataset we used to train our story emotion classifier. Basically, the dataset is the same. It's called the Call of the Wild, and it's organized as an ordered sequence of sentences labeled according to a model of emotion. The difference now is that we map our previous categorical model of emotion into a valence and arousal model. So for example, the label calm is now represented as the pair 1, 0. This means that calm has values of valence 1 and arousal 0. Let me now talk about the model we use as our story emotion classifier. Here, we fine-tune a high-capacity BERT architecture with the Call of the Wild dataset. The way it works is we take a sentence, for example, with a certain value of valence, and we feed that into a pre-trained BERT. We then use a new dense layer, which is a classification head, to predict the value of valence. We do exactly the same for arousal. So we actually duplicate the pre-trained BERT, we have a new dense layer, and then we can predict the value of arousal. We then combine these two predictions to form the final output, which is the emotion of the given sentence. In Bardo Composer, we also have a music emotion classifier, and it works similar to the story emotion classifier. But here, we pre-train a high-capacity GPT-2 language model with a new dataset we created, called ADL Piano MIDI. It works by taking music pieces and encoding them as strings using an encoding system that we designed. We then feed those strings into the language model to get the probability of the next token in the sequence. After pre-training the GPT-2 architecture as a language model, we fine-tune it using the VG-MIDI dataset. And this works similar to the story emotion classifier. So here we have a music piece with a certain value of valence. We feed it into the language model. We have a dense layer to predict the valence value. And then we also have a copy for the arousal dimension. We combine these two predictions to form the final output. With both the story and the music emotion classifiers, we can now talk about the stochastic bi-objective beam search, which is the main contribution of this paper. It starts by taking the current story caption and feeding that into the story emotion classifier to get a desired emotion. In this case, E equals to 0, 1. We then take the initial music tokens, for example, X with 2 tokens, and we feed that into the language model, and we get the probability of the next token in the sequence. Using this probability distribution, we select the top case sequences and we feed them into the music emotion classifier. What we get is the probability distribution of each of these top case sequences being of valence equals to 0, and the probability of these top case sequences being of arousal equals to 1. We then combine or multiply those two probability distributions with the probability distribution given by the language model, and the resulting distribution is used to sample our beam of size B. In the second iteration of the beam search, we start with B sequences, and each sequence has 3 tokens. It's important to highlight that the emotion hasn't changed because we are still composing for the same piece of speech. So we feed all these B sequences into the language model, and now what we do is we concatenate for each branch of the beam all the possible V events in our vocabulary of musical events. Then, out of all these possible sequences, we select the top case sequences. And we feed those into the music emotion classifier. And again, we get the probability distribution of valence equals to 1, the probability distribution of arousal equals to 1. We combine those two with the probability distribution of the language model, and the resulting distribution is used to sample the next beam. This beam search is executed until we find one sequence in the beam that has length equals to the piece of speech that we are trying to generate music for. We call this algorithm stochastic because the beams are created using a stochastic approach, and we call it bi-objective because we combine the probability distributions from the language model with the distribution from the music emotion classifier. Let me now present our experiments. We first analyze the accuracy of our story emotion classifier, and we do this analysis on each episode of the Call of the Wild dataset. Here, we use a leave one out approach. This means that if you're testing for episode 1, we did the training using episodes from 2 to 9. And we compare our approach against the naive Bayes method used in the original Bardo paper. So looking at the valence dimension, naive Bayes had an accuracy of 80% in average. Our BERT method beat the naive Bayes approach in every single episode, having an average accuracy of 87%. Now considering the arousal dimension, naive Bayes had an average accuracy of 83%. Our BERT method again beat the original naive Bayes on every single episode, and we had an average accuracy of 88%. We also analyzed the accuracy of our music emotion classifier. And here we compare the GPT-2 approach against the LSTM method. For both of these methods, we compare the baseline and the fine-tuned versions. The baseline versions, they were trained only on labeled data, whereas the fine-tuned versions were pre-trained on unlabeled data. Looking at the results, we can see that the fine-tuned GPT-2 outperformed all the other methods. Comparing the baseline and the fine-tuned versions of the GPT-2, we can see that for valence, we got a boost of 10%, and for arousal, we got a boost of 8% accuracy. In our last experiment, we ran a user study where we asked human subjects to listen to music pieces containing one emotion transition in them. And we asked these subjects 2 questions. What is the emotion that you perceive in the first part of the piece? And what is the emotion you perceive in the second part of the piece? So this user study was designed with 2 independent groups A and B, where each group was composed by 58 participants. Group A listened to composer pieces, and Group B listened to baseline pieces. I'm going to describe what this baseline method is in a bit. Before, let me talk about the pieces. Each piece contains exactly one emotion transition, and they are on average 20 seconds long. And each piece was generated for a different Call of the Wild episode. So the baseline method works as follows. Whenever there is an emotion transition, a human composed piece with the target emotion is selected at random from the VG-MIDI dataset. This table shows the result of our user study. And here we have the 5 pieces labeled E1 till E5 for each method, the baseline and composer. Remember that each piece has 2 parts, P1 and P2. And we report for each piece the valence and arousal dimensions independently. Each cell of the table represents a percentage of participants that correctly identified either valence or arousal intended by the methods. Looking at the results, we see that for the first episode, composer outperformed baseline on part 2. On episode 2, composer also outperformed the baseline, but now in part 1. In episode 3, Baseline outperformed Composer in both the parts. In episode 4, Baseline outperformed again the Composer on part 2. And on episode 5, Composer outperformed Baseline in part 1. This table shows the average results of our user study. And here we report the average for valence, arousal, and valence and arousal combined. Looking at the results, we can see that both methods pretty much perform the same. So we can conclude that human subjects, they were able to identify emotions in pieces generated by Composer as accurately as they could identify emotions in pieces composed by human composers. Okay, that was our last experiment, and now with the fun part, let me show an example of a piece generated by Composer, and this one has a transition from agitated to suspense. As a conclusion, I just want to recap that we propose here Bardo Composer, which is a system that generates background music for tabletop RPGs. As part of this project, we introduced stochastic biobjective beam search, which is a new algorithm that we use for controlling the emotion of pieces generated by language models. And finally, we showed through a user study that subjects can recognize the emotion of generated pieces as accurately as they can identify the emotion of pieces composed by humans. Thank you very much. So feel free to contact me and also to check out our GitHub page for more information and more pieces.